Okay, welcome back. This is 30 Gang. Unit 1 Kinematics and Dynamics. Part B, Vector and Scalar Quantities, Part 1. So Section B, Part 1. So of course this pertains to pages 11 to 19 of the Duotang. And if we look at the objectives for this, here we're going to look at the beginning parts of vectors. So define and provide an example of vector quantity, scalar quantity, equivalent vectors, and collinear vectors, and also represent vector quantities on neat, accurate scale diagrams using rulers and protractors. So if we start the questions here, how are vector quantities visually represented? So if you look at a variable x or v, how do you know it's a vector quantity? Well, you use a half arrow over top of it. For example, if this arrow here represents a vector, we would call it something. Could call it v, could call it x, call it y. Just don't call it lonely. And then we have a half arrow over top of it. So that's usually the common practice used for that. How are magnitude and direction illustrated using the idea from part A? So a vector quantity has to have two things. It has to have a magnitude or a size, and that's illustrated by the length of the arrow. And then of course whatever way the arrow is pointing is its direction. And though there are quite a few different ways we can illustrate that, I like to use the north, south, east, west map directions to illustrate that, as we'll see in the upcoming examples here. A few key points here. The origin of a vector is otherwise known as the starting point of a vector. It's also sometimes referred to as the tail of the vector. And then the terminal point of the vector is referred to as the ending point of the vector, or sometimes called the tip or the head. So usually head, tail. The arrowhead part is the head, and the starting point is the tail. A vector can be represented by a variable. What must be done? So we talked about this already. So a half arrow over top of a variable that you choose to name it. And then of course the two things that a vector quantity must have is a magnitude, size, and also which way is it pointing or direction, as illustrated earlier. And then to do that, the magnitude, for now we'll be using scale diagrams using rulers and protractors, so you'll have to figure an appropriate scale to use on your piece of paper. If you're representing a vector that's 2 kilometers in length, obviously you're not going to draw 2 kilometers. You're going to have 1 centimeter on your paper equivalent to something in real life that you're trying to illustrate. And of course direction, you measure that with the protractor. If we take a look here, so the map directions, or the direction of the vector, I like to illustrate like this. So for example, south 28 degrees west. To interpret what's happening here is that if this is the starting point, this is a movement in this particular direction. So starting straight south, moving 28 degrees in the west direction. So if you were to sketch that, it would look something like this. If this arrow had been starting straight south and it's attached here, its tail's attached to the origin, move it 28 degrees in the west direction. So that is how that illustrated. And of course, those of you taking pre-calc math, quadrant 1, quadrant 2, quadrant 3, south 28 west is equivalent to west and moving 62 degrees in the south direction. So of course these two angles add up to be 90. So with vectors there will always be 2 possible directions depending upon what quadrant it is in. There's always 2 ways you can explain it, and it doesn't matter which way you use, west 62 south or south 28 west. Either one will work fine. So if we look at drawing a few vectors here, use appropriate scales to draw the following vectors. Be sure to state the scale used and then accurately draw the scale, or sort of the vector, using a ruler and protractor. So here vector A, I think I forgot to write the little vector half arrows over top, so if you could include that, that'd be great. So we're representing something that's 5 kilometers. Now 5 centimeters is big enough on your paper, so you may wish to use a scale. 1 centimeter on your paper is 1 kilometer in the real world. If we look at 12, we could do 1 centimeter on our paper equals 12 meters, or 1 meter, I suppose, and it ended up being 12 meters. But I just chose to do it 2. You don't want your vector diagrams too small, and you don't want them too big. The first part of the scale is always what's happening on your paper, and the second part is what is it pertaining to in the question. So if we look here, if 1 equals 1, then to get something that's 5 kilometers, you can see 1 times 5 is 5, 1 times 5 is 5. So 5 centimeters, 5 kilometers. If I look at this example here, if I did 1 centimeter equals 2 meters, I'm trying to make something that's 12 meters, so relating that to 12, you can see it's multiplied by a factor of 6. So this has to be multiplied by a factor of 6. So 1 to 2 is equivalent to 6 to 12. So 6 centimeters on my paper represents 12 meters in the real world. So if we look there, now you can draw yours. I just kind of sketched them here using this ruler here. So a starting point, and it's good if you have a piece of loose leaf behind your paper because you can get the east-west directions good. And so I drew this 5 centimeters, and then don't fall in the trap of spending all your time making this perfectly 5 centimeters and then messing up drawing the arrow. Make sure the arrow is nice and neat with the tip at the tip of that line right there. Okay, and over here, so I'm drawing it 6 centimeters long, so if I was to measure this, hopefully it's 6. And and of course to draw the direction right, so yeah, you can see it's 6 approximately, west 30 south. So from straight west, measure with your protractor going 30 south. And here I have a protractor. I'll just kind of illustrate how to measure that in case you forgot. So wherever you're starting with in your direction there, so here starting west, so that's my 0. So I'll put my 0 of my protractor pointing in that direction. 0, 10, 20, 30. So you can see it goes right to the 30 mark on the protractor. So starting point 30 south. So it tells you what direction. Okay? I'll have you take a look at these and draw them. Maybe press stop on the video and then come back to the video and see how you did. So we want to represent vector C being 24.0 meters east 45 south, and D 150 kilometers north 25 degrees east. Okay, so you may want to pause it right here and just try to draw that. There's more than one way you can do it. There's more than one scale you can use. I chose to do 1 centimeter equals 4 meters. And you can see here 24 is divisible by 4 6 times. So multiplied by 6, multiplied by 6. To represent 24 meters, I'm going to draw it 6 centimeters long. This one here, 150 kilometers. So and once again, you want these diagrams to be around 4 to 10 centimeters on your paper. So 1 centimeter equals 25 works. I suppose I could have done 1 equals 50, then I'd have to make it 3 centimeters. Doesn't really matter, as long as you get the right answer and not have them too small. So times 25 times 6 is 150. So 1 times 6 is 6. So 6 centimeters is going to be this one, and 6 centimeters for this one. So drawing those out, I just sketched mine kind of roughly. Yours hopefully looks better than mine. So mine's going to have a length of 6. And take a look here. East. So from straight east, and notice there's 2 scales on a protractor, an inner one and an outer one. So I'm using the outside scale this time. East, 10, 20, 30, 45 in the south direction. Okay. Looking at this one, I'm making it 6 centimeters long as well. But this time I'm starting in the north and going east. So again, north, my protractor is going to start off with north, so that's going to be my 0, then going 25 in the east direction. So it makes sense to have your protractor aligned like this and not like this, for example, because if I had my 0 scale pointing at north, I'd be going in the west direction. So be careful with that. Make sure you get those map directions correct. And lastly, we have some vocab to wrap things up. So we looked at vector quantity. That's something that can be a quantity that can be completely described with the magnitude and direction. So I just drew an example here. Vector R, I could call it anything you want. 10 meters east, 30 north. Scalar quantity is only something that can be described with magnitude only, so size like vector, but no direction, because it doesn't make sense to have 5 kilograms in a particular direction or 3.5 seconds in a particular direction. So scalar quantities, magnitude only. Equivalent vectors, so they have to be the same in every which way. They have to be the same length and the same direction. So same size and same direction. They don't have to have the same starting point. So you can see here B is starting off slightly to the right of A. As long as they're the same magnitude, same direction, they are therefore equivalent vectors. And last thing here we have collinear. And you notice the word collinear has the word line embedded in it. So vectors that are in the same or opposite direction from each other. They share the same line. So for example, east, west share the same line, north, south share the same line. So these vectors here, vector A going 5 meters east, vector B going 2 meters west would be collinear. Or I could have had an example, 2 meters north, 3 meters north, they are collinear as well. So they share the same line, they can be in the same direction or opposite direction. Okay, so that is that assignment. We'll see you next time.